Hey everyone, welcome back to linear algebra. This will be lecture 12 of the course. In this section, we're going to get into a very interesting area of linear algebra, and that's going to be eigenvalues and diagonalization. And so what we will be doing primarily, we'll start by defining eigenvalues and a kindred concept, eigenvectors, and these will be defined in the context of matrices. And the goal of the section will be to use eigenvalues and eigenvectors to find a diagonal form for a square matrix. So the second half will be the discussion of diagonalization. All right, well, let's go ahead and jump into it. And so we'll call this section 3.4 Eigenvalues and Diagonalization. Okay, and so I think it makes sense to go ahead and start by defining what we mean by an eigenvalue. And so this is a notoriously challenging section for students. And so we're going to try to just kind of take it slow and make sure that things are well understood. So we're going to let A be an n by n matrix. Okay. Then we say that a real number, right? So just a real number, like a scalar, a real number, and the notation we usually use for eigenvalues is lambda from the Greek alphabet. A real number lambda is an eigenvalue of A It's an eigenvalue of A if and only if there is a non-zero n vector x a non-zero n vector, we'll call it x for now, such that A times the vector x is equal to lambda times the vector x. Okay, so that's what we mean by an eigenvalue. So an eigenvalue is a real number that, when multiplied by a specific vector x, produces the same vector as the entire matrix A multiplied by the vector x. Okay, and so kind of to go along with an eigenvalue, we usually have to talk about an eigenvector, and these vectors x, those are eigenvectors. And so we say that any non-zero vector x for which ax equals lambda x is called an eigenvector. So an eigenvector, and we usually have to have the eigenvectors corresponding to some eigenvalue. So this particular x would be an eigenvector corresponding to the eigenvalue lambda. To the eigenvalue lambda. Okay? So that's what we mean by eigenvalue and eigenvector. Okay, so this relationship, you've given A, given n by n matrix A, lambda is an eigenvalue if there exists an eigenvector x such that A times the vector x, which is a vector, right? This is n by n, this is n by 1, so the result is n by 1. So A times x, that vector, is going to be equal to the scalar lambda times x. Okay, so that's kind of a more, maybe a slightly more concise, but maybe less rigorous way to say it. Basically, lambda's a real value that produces the same vector when multiplied with x as A does. Okay. So eigenvalues and eigenvectors are sometimes called characteristic values and characteristic vectors. So eigenvalues slash vectors are sometimes called characteristic values slash vectors. And I think most of the time now, anyways, I would think that eigen is the more common usage, but I could be mistaken on that. So, important things to note, okay? So note a couple of things. Eigenvalues may be 0. Okay, eigenvalues may be 0. Okay. However, eigenvectors can never be 0. That's just the definition, right? Eigenvector has to be a non-zero vector. Eigenvalues may be 0, though. Okay. All right, and so what does this mean when we say a times x equals lambda times x? What does that mean? Well, it says that the matrix product ax, so the matrix product ax, which is a vector, is equivalent to the scalar product lambda x. So this is a matrix product, right? This is matrix multiplication, and this is just a scalar product. Okay, so it's important to note, right? It's important to note. Right, so ax is a matrix product, lambda x is the scalar product, and so what that implies is that, ax, this is a vector, right, when multiplied together, that vector is parallel to x. Okay, it's parallel to x. And what we can say is that when we dilate x or contract it, when we dial it up or down by lambda, they become equivalent. Right? So ax is parallel to x, and then dilating x or contracting x. Right? And the way to think about that is all based on the value of lambda. So if lambda, the absolute value of lambda is greater than 1, then we're going to be dilating. But if the absolute value of lambda is less than 1, then we're going to naturally be contracting. Okay, so dilating is when lambda is greater than 1. Contracting is when lambda is less than 1. So shrinking, stretching, another way to think about it, in other words. Right, and so you can kind of think of eigenvalues as having this sort of geometrical quality. Right, so you've got your x, which is parallel to ax, and lambda stretches or contracts it. Okay, all right. So let's do an example here. Let's talk through an example. We'll use this example throughout the lecture, so let's take our time, make sure we understand this. So consider 3 by 3 matrix here, and we're going to say it's -4, 8, -12, and then 6, -6, +12, and then 6, -8, 14. Right? So that's going to be our 3 by 3 matrix. And so we'll talk about how to find the eigenvalues in a bit, but let's just say it right now that lambda equal to 2 is an eigenvalue for A. Okay, and specifically because there's a vector x, which is 4, 3, 0. Okay, and so lambda equals 2 is an eigenvalue for A because x equal to 4, 3, 0 is an eigenvector. All right, so notice what are we going to say here? Well, we're going to say that A times the vector x is going to produce some vector. Let's figure out what that is. So we can multiply these together. Right, so we can just multiply these together. And you can do this, right? So it'd be negative 4 times 4 plus 8 times 3 minus 12 times 0, right? And when you do that, you'll get 8, 6, and 0. So take your time, pause the video if you need to, and make sure that this multiplication works, right? And you know that exactly where these quantities are coming from. Okay, now the eigenvalue is 2 and this is an eigenvector corresponding to lambda equals 2. And so it better be true that this eigenvalue of 2 times 430 is equal to 860. And that's obviously true, isn't it? 2 times 4 is 8, 2 times 3 is 6, 2 times 0 is 0. And so that's our lambda times x. Right, so this is a very clean example of an eigenvalue eigenvector relationship in some matrix A. Okay. Now, it turns out that this eigenvector of 430 is not the only eigenvector corresponding to lambda. Right? So what we would say is actually any non-zero scalar multiple of x, any non-zero scalar multiple of x is an eigenvalue of A corresponding to this lambda. Is an eigenvector, sorry. Is an eigenvector of A corresponding to lambda equals 2. Right, and why is this? Is this mysterious? Hopefully not, right? You can think about it like this. If I have my A times some constant times x, right? Then, I mean, this is a scalar, this is a matrix, this is a vector, right? So the scalar can come out front, can it? I could go like this, right? And so this I know is equal to c times 2x, right? 2 being the eigenvalue, right? It can take the place of A when we're multiplying with x. And so you can see that this is equal to 2 times basically any scalar multiple of x. So there are infinitely many eigenvectors corresponding to lambda equals 2. Right, infinitely many. Okay. Right, so for example, I could replace 430 with 860 as the eigenvector. That's just 2 times it. And if I plug in 860 here and I plug in 860 here, then I'm going to get some new vector when I multiply ax. I'm going to get some new vector when I multiply lambda x, and they should be the same. Okay. Right, so there's an infinite number of eigenvectors corresponding to lambda. This is true in general. Right, and so let's define what we mean by the eigenspace. So we'll let A be an n by n matrix, and lambda be an eigenvalue of A. Okay, then the set, and here's how a lot of times it's denoted as just a capital E with a subscript lambda, whatever the eigenvalue happens to be. E lambda equal to the set of all vectors such that ax equals lambda x. This is called the eigenspace of lambda. Right, and this eigenspace is the set of all vectors associated with lambda, right? And this is going to naturally include the 0 vector. Right, so strictly speaking, E is not merely a space of eigenvectors, right? there's always going to be one vector in there that technically is not an eigenvector, and that's going to be the 0 vector, right? And that should be obvious, right? Because a times the 0 vector is going to be equal to lambda times the 0 vector. Okay, so while 0 is not an eigenvector, it is part of the eigenspace. Okay, and that's just by the way it's defined. Okay. All right. Very good. Very good. Okay, so just to kind of drive that idea home, we just had this matrix A, and we found that lambda was equal to 2. And we had a specific eigenvector that we identified. And so what we could say is that the eigenvector corresponding to lambda equals 2, or sorry, the eigenspace corresponding to lambda equals 2, is going to be the set of all x such that x is equal to c times, we found a representative 430 vector, such that c is a real number. So that's going to be the eigenspace, right? And so obviously 0 is going to be fine because c equal to 0 will produce that vector. Now it turns out that this may not be all of the eigenvectors corresponding to 2. Okay, so there may be more. There may be some that are not strictly a linear or a scalar multiple of this given vector. There may be additional. And we'll talk more about that in a moment, but I just want to point out that there may be more, right? So I don't mean to write equals there, I mean to write union. Okay, so the eigenspace can be larger. Okay, so it's going to include all of this infinite variety of vectors here, but it also could be larger. Okay. All right. Very good. Okay. All right, so that's just kind of basically all we've done so far is we've defined what we mean by an eigenvalue. We've defined what an eigenvector is. We've looked just at a simple example of an eigenvalue-vector relationship, and we've determined that there are, for a given eigenvalue, there are infinitely many eigenvectors. And those are going to generally have the form of being a scalar multiple of whatever the given eigenvector is, in this case 430. Right? But there could be totally distinct eigenvectors that can't be derived in this fashion, right? And so we'll get into that a little bit later. What we want to do first, before we get heavy into the eigenvectors, we need to figure out how do we identify eigenvalues? How to identify eigenvalues, right? So what's the technique? What's the method that should be employed? All right, we're just going to kind of derive something here. So let's say given A, the matrix A, and lambda and an eigenvector x. Right, so we're going to start with just the ingredients here. So we know that A times the eigenvector x is equal to lambda times the eigenvector x. Okay. And one way to think about this lambda times x over here is you could write this as lambda times the identity matrix times x. I'm just going to put that kind of in parentheses there, like that. So make sure that you see that this can be done, right? Take a representative vector and make sure you understand that you can write multiply by the identity matrix. Okay, and so this exists, right? So this is true, right? And so what I can do is I can subtract this whole operation here and kind of bring it over to this other side. Let's not worry about this intermediate step right now. So I've got A times x minus lambda times ix equals 0. And this would be the 0 vector, of course. Okay, and we can factor out the vector x, right? And so I would have, you could write it like this, a minus lambda I times the vector x equals 0. Right, and so this looks a bit like a system, doesn't it? You've got some kind of a matrix here times a vector is equal to 0. And so then what we could say is that x, in this case, is a non-trivial solution. Well, hold on, is a non-trivial solution to this homogeneous system. To the homogeneous system, right? And in this system, the coefficient matrix is played by A minus lambda I. Okay. All right, so you've got this kind of way to think about it as a system. Okay, so, similarly, we could go the other way, and frequently books will differ in how they notate these things. So similarly, you could say, you start from AX equals lambda IX, right? Just kind of stepping back to that. Then I could subtract this guy from both sides, kind of bring it over here, right? And so that would mean that the 0 vector is equal to lambda I times x minus AX. Okay, and this is going to be the direction that we'll prefer, right? And so what this, I'm just going to flip the order here, but this is basically saying that lambda I minus A times x is equal to 0, right? So you see that just the order is a little flipped here. Not a problem. All right, so okay. And so the solution that gets generated here should be the same in both cases. So the solution to A minus lambda I times x equals 0 is the same as lambda I minus A times x equals 0. Okay, so just to note that, it doesn't matter the direction you go. Okay, and so this is going to be the mechanism that we're going to use to find our eigenvalues. Okay, and this will be the mechanism we use to find our eigenvalues. Okay, and vectors. Okay, so let's write this out in more formal terms, like as a theorem. Okay, so theorem. We're going to let A be an n by n matrix. Let A be an n by n matrix, and let lambda be a real number. Okay. Then we say lambda is an eigenvalue of A. So it's an eigenvalue of A if and only if the determinant of lambda times I minus A is equal to 0. The eigenvectors corresponding to lambda and the eigenvalues corresponding to lambda are the non-trivial solutions. They're the non-trivial solutions to the homogeneous system to the homogeneous system, which we talked about just a moment ago, lambda I minus A times x equals 0. Okay, and then technically we would say that the eigenspace is the complete solution set for the system. And that makes sense, right? Right, so this whole mechanism is basically falls back on the theory that we laid out of homogeneous systems. You know, finding your eigenvalues and your eigenvectors is just a matter of solving a very particular homogeneous system. Okay, so let's go ahead and do an example here. All right, let's try an example. We're going to let A equal our running example. So -4, 8, -12, 6, -6, 12, and 6, -8, 14. Okay, so we've got this matrix A. We know that lambda equals 2 is an eigenvalue. Let's see how we can get to that. Okay, let's see how we can get to that. So we need to find the determinant of basically 2 times I cubed minus A. Okay, and so we can plug in 2, 0, 0, 0, 2, 0, 0, 0, 2. That's 2 times I. Minus, and then A, we just wrote it out, but let's write it out again, just to be clear. Right, like so. And so when we do this subtraction, we get 6, -8, 12, -6, +8, 12, -12, sorry. And then -6, 8, -12 again. Okay, so we've got this matrix, and we want to find the determinant of this. Now, what is the determinant? The determinant is equal to 0. Okay, you can see that, and we know the determinant is equal to 0 because two of the rows are basically identical. Two of the rows are identical, right? And so if you think back to when we talked about the determinant, if you look back, you'll find that that was the theorem that indeed that the determinant was equal to 0 if two of the rows were identical. Okay, and so this shows you that 2 is indeed an eigenvalue of this matrix. Okay. All right, now what about the eigenvectors that correspond to lambda equals 2? What about the eigenvectors corresponding to lambda equals 2? How can we identify those? Well, remember, what we had to do there was we had to solve a system, right? So the system we need to solve, it can be represented by an augmented matrix that looks like this. So 2 times I minus A augmented with 0. So it's a homogeneous system, right? Okay, and so we can easily do this, right? So we know what 2I minus A looks like. It's basically this matrix right here, right? So you've got 6, -8, 12, -6, 8, -12, and then -6, 8, -12 again, and then 0, 0, 0. Right, and this would take you only a few moments to realize that this can be row reduced down to something with 2 full 0 rows. Right, it turns out that this can be row reduced down to 1, -4/3, 2, and 0, and then these rows are 0, 0, 0, 0. Right, and so you can row reduce it down to this system right here. Okay, and now we just need to pull a vector out of here. We need to find a particular solution. And so what can we do? Well, we can write this first line as x1 minus 4/3 x2 plus 2x3 equals 0. Right, and we can just let x2 equal some number a, and we'll let x3 equal some number b. Okay, and so that means x1 is going to be equal to 4/3 a, right, taking this to the opposite side, minus 2b. Okay, so you've got your x1, you've got your x2, you've got your x3. And so E2, at least partially, is going to include the vectors. So it'd be 4/3 a minus 2b, comma, a, comma, b, such that a and b are real numbers. All right, and there may be more, so I'm going to put a... Right, so this is a way to, once you have your eigenvalue, you can go and quickly find an eigenvector. Well, quickly. I shouldn't say it's quick. It's not necessarily quick, but this is a mechanism you can use to go and find an eigenvector. You basically set up this homogeneous system, solve it, find the solution set to this homogeneous system, and that's going to be at least part of your eigenspace. Okay, and so this, because we started with a matrix that we've already looked at, how would we get back to our 4-3-0 example? Right, so in our previous example, we saw for lambda equals 2 that, you know, our representative eigenvector was 4-3-0. How do we get back to that? How do we get back to that specific one? Well, if our vectors have the form 4/3 a minus 2b, comma a, comma b, we can just set a equal to 3 and b equal to 0, right? And that should produce the vector that we're used to seeing. So you got 4/3 times 3 minus 2 times 0, comma 3, comma 0, which is, you know, you get the cancellation there, so you get your 4-3-0. So this is our eigenvector that we saw originally in our example. But we know that there are others, and here's how we can derive them. Okay. All right. Great. So let's see. So far in this example, we haven't really talked about how to find the eigenvalue. We kind of just operated from the standpoint of 2 being an eigenvalue. So given that, how do we find the eigenvectors? But how do we actually find all the eigenvalues? Like, what's the mechanism, right? What's the mechanism to find those eigenvalues? Well, to find all the eigenvalues, there are different approaches you can take, but to find all the eigenvalues for A, usually the most elementary sort of approach to this is to do the following. To find all the eigenvalues for A, we set the determinant lambda I minus A equals 0, and we solve for lambda. Right. So before we said, hey, look, you know, if to find the eigenvectors, we need to first figure out what lambda I minus A is, and then we set up a system where that's the coefficient matrix. But now we're saying, look, I don't know what lambda is. Here's how do I figure out what lambda is? Well, the way you do it is you set up this matrix and identify the determinant, right? And that's got to be equal to 0, right? So this is going to produce a very particular kind of equation, which we'll define in a moment. But let's actually just do an example of this with our 3x3, right? So remember, A was equal to -4, 8, -12, 6, -6, +12, 6, -8, 14, right? So this is our example. Okay. And so let's set up our equation. So we need to basically set up this equation. So 0 is equal to lambda I minus A, the determinant of that matrix, which is what? Well, you've got the lambda matrix. Lambda times I is lambda 0, 0, 0, lambda 0, 0, 0, lambda. That's the identity matrix times a scalar lambda, minus A, which is this guy, negative 4, 8, negative 12, 6, negative 6, positive 12, 6, negative 8, 14. Okay, and so when you do this, what do you get? You get lambda plus 4, 0 minus 8, and 0 plus 12. Okay, so you see you end up with this lambda plus 4 here. Right, and then you go 0 minus 6, so negative 6, and then lambda minus negative 6, so that means lambda plus 6. And then 0 minus 12, so negative 12 there, and then negative 6, 8, and then down here you get lambda minus 14. Okay, we need to find the determinant of this matrix. Well, you just treat this like any old matrix and calculate the determinant. Right, now what you'll end up doing, of course, is using the regular formulas for identification of the determinant. So you'll have the block that out, find the determinant of that submatrix, then block those two out, find the determinant of that submatrix, then block those two out, find the determinant of that submatrix. And when you do that, when you do all of that, you get something that looks like this: lambda cubed minus 4 lambda squared plus 4 lambda. Okay, and so again, this is going to require a lot of simplification, and you have to remember to follow, the formula with the cofactors, and just choose a row to do a cofactor expansion across, and you'll get a big old algebraic mess, and then it simplifies down into this cubic equation. All right, so what do we have here? We have lambda cubed minus 4 lambda squared plus 4 lambda equals 0. And this is actually factorable, right? You can factor this, and what you'll see is that this is lambda. So if you factor a lambda out, you get what? Lambda squared minus 4 lambda plus 4, right? And then this is factorable as well, and what you'll find is you get lambda minus 2 quantity squared equals 0. Okay, and the solutions then to this equation are the eigenvalues. Okay, they're the eigenvalues. So one of the solutions is lambda equals 0. And the other one is obtained by this, lambda minus 2 squared equals 0. And so the other one is lambda equals 2. And so this is the one we've been running with. Turns out there's a second eigenvalue, and that's the eigenvalue 0. Okay. Now we usually want to label these in some way. And I think the convention is to have them labeled in descending order. Okay, so you've got your two eigenvalues. Lambda 1 is 2, lambda 2 is 0. Okay? So we have an eigenvector for lambda equals 2. Let's go find an eigenvector for lambda equals 0. How would we go about that? Well, it's going to be the same operation as we previously saw, just the only thing that's changed now is the eigenvalue. How to find an eigenvector for lambda equals 0. So that's our second eigenvalue. We'll say, well, it's the same thing, right? So you're going to take 0 times the identity minus A. It's going to be an augmented matrix representing this homogeneous system where lambda I minus A is the coefficient matrix. In this case, the eigenvalue is 0, so the only thing that changes is A's, all the signs flip. All right, and so you got 4, negative 8, 12, negative 6, 6, negative 12, and then negative 6, 8, negative 14. Right, and this is a homogeneous system, so The scalar part of the augmented matrix is 0. And you could row reduce this. I encourage you to pause the video, make sure you know how to do that, make sure you can get to what you need to get to, but you'll find that the system will row reduce to 0, 1, 0, 1, 0, 1, negative 1, and then 0, 0, 0. Right, so it looks like this. And you can extract from this what the eigenvalue must, or the eigenvector must be, right, or the form of the eigenvector. Right, and so the solution set here, solution set is going to be the eigenspace for 0. Turns out it's going to be C times the vector negative 1, 1, 1. Right, and of course this representative vector you identify will vary depending on what you choose for your independent variable here, but I've obviously chosen 1. And when you choose 1, it forces x2 to be 1 and x1 to be negative 1. Right, but yours may vary, but they'll all be just scalar multiples of one another. Okay, and so this is the eigenspace for lambda equals 0, and we can confirm. Right? How would we confirm that this is an eigenvector and that lambda equals 0 is an eigenvalue? Well, I mean, the way we identified them kind of is confirmation enough, but we could just do the multiplication here, right? We could multiply this out. 6, negative 6, 12. 6, negative 8, 14. Right? Multiply that times negative 1, 1, 1. And what you find out is that this actually equals 0, 0, 0, which is all it can equal because the eigenvalue is 0, right? Okay, and so this is our lambda x. All right, perfect. Right, so that's the idea with eigenvalues and eigenvectors. So an eigenvalue slash vector has this relationship, a times x equals lambda times x. Right, so then to find eigenvalues, we need to solve, what do we need to solve? Lambda I minus a, that determinant, equals 0. That's what we need to solve. Okay, so this is a determinant, which means it's not a matrix. It's a matrix that you're taking the determinant of. When you do that, you'll get an equation, a very particular equation, which we're about to define. And the solutions to that equation are the eigenvalues. How do we find the eigenvectors? Right. Well, that's going to involve solving a system. Right. What's the system? Well, it's lambda times the identity minus a augmented with the 0 matrix. Okay, so solving a system will produce a vector, and that vector is going to be the representative of the eigenspace. And there's an infinite variety of eigenvectors, but you just need one. Okay, so that's what we've got so far. Okay, now in practice, eigenvalues can be very challenging to identify. They can be really tricky. Right? It just really depends on the matrix, right? And so, you know, as your matrix dimensions grow, then this becomes really complicated, right? Identification of the determinant can be very complicated. You know, if it's a 5 by 5 or a 6 by 6, it's going to be very involved. But whatever mechanism you can use to solve that determinant, you know, if there's a faster way to do it, a better way to do it, then do it. A lot of times you'll just rely on computational aids, or you know, to assist you with finding these eigenvalues. In the case of a 3 by 3, you can definitely do it yourself, though. But then once you've got the equation out of this form, then you have to solve that equation, right? So naturally that can be tricky depending on the equation. The system is more straightforward. This is more straightforward. It's just set up the matrix, the coefficient matrix, and then it's just a row reduction exercise, isn't it? Of course, if it's a big system with lots of variables, lots of rows, it can be more challenging as well, right? So, but in theory, this is how it is done. Okay, let's talk more about this. Let's talk more about this, and specifically, let's talk about the equation that is produced by this setup here, by this determinant equals 0 setup. So definition, if A is an n by n matrix, then the characteristic polynomial of A is the polynomial that we've been talking about this whole time. It's called the characteristic polynomial. If A is an n by n matrix, then the characteristic polynomial of A is the polynomial, and it's denoted with a P sub A. That's the characteristic polynomial of A is going to be equal to x times the identity, the n by n identity, minus A. Okay, and so this equation has a name. It is called the characteristic polynomial. Well, that's the one side of it. And this is the characteristic polynomial here, but lay it into this equation format. When you set the characteristic polynomial equal to 0, the roots of that equation are the eigenvalues of A. Okay, and so obviously if A is n by n, you can probably guess what the degree of the polynomial ought to be. So if A is n by n, then P of A is nth degree. Right, so it's an nth degree polynomial. And how many distinct roots will the characteristic polynomial have? Okay, well, P of A will have at most n distinct roots, distinct real roots. Some of the roots may be complex roots, right? Those are not eigenvalues. Only the real roots are the eigenvalues. If I didn't say that before, I meant to say that. The eigenvalue has to be a real number. I did say that for sure. So some of the roots of this polynomial could be complex, right? So they could be imaginary numbers, not real numbers. We don't consider those to be eigenvalues. All right, so P of A has at most n real roots, right? Like in the example we saw previously, we had 2 real roots. It was a 3 by 3 matrix. The characteristic polynomial was indeed a 3rd degree polynomial, but we only had 2 distinct roots. And so you could, if you recall what that polynomial looked like, let me find it. What did it look like? Yeah. Our previous example looked like this: lambda cubed minus 4 lambda squared plus 4 lambda, right? And we were able to factor that down to lambda times lambda minus 2 squared. Okay, and then if we set that equal to 0 and solve, we found lambda equals 2 and lambda equals 0. So this is obviously a repeated root, right, because of the 2nd degree exponent there. Okay. Yeah, and so I mean basically what this all kind of boils down to is that the eigenvalues of A are precisely the real roots of this characteristic polynomial. I mean, I know I've said that in several ways, but let me just state it plainly. The eigenvalues of A are precisely the real roots of the characteristic polynomial of A. All right, that's fascinating, right? So this very special number called the eigenvalue comes out of this particular matrix that we have to identify the determinant of, which produces the determinant of this particular matrix that produces something called the characteristic equation, and the roots, the real roots of the characteristic equation, turn out to be the eigenvalues. So there's a deep, obviously very deep structure that we're uncovering here with this eigenvalue stuff. Let's do an example. Okay, so let's make a slightly smaller example so we can work it from end to end. So we'll let A equal this 2 by 2, so 12, negative 51, 2, and negative 11. So it's a 2 by 2 matrix. We want to find the characteristic polynomial. Okay, so we know that that's going to be equal to the determinant of, basically a lambda, 0, 0, lambda, minus A. Right? So whatever lambda happens to be, lambda times I is this, and A is 12, negative 51, 2, negative 11. Okay, and so we can run through this and we get lambda minus 12, and then we get 51, right? Negative, negative, right? So it flips. And then you get negative 2, and then lambda plus 11. Okay. And so what happens when we calculate the determinant? Well, the determinant of a 2 by 2 is super easy, right? It's just the diagonals minus the other diagonals. All right, so what we see here is we get x minus 12 times, lambda minus 12 times lambda plus 11 minus negative 2 times 51. Right, and can we simplify this? Yeah, we get lambda squared plus 11 lambda minus 12 lambda, and then 12 and 11, that makes a minus 132, and then this is plus 102. Right, 51 times 2 is 102. Right, and so we can simplify this. We can simplify this down, and so we get lambda squared, and then I've got 11 minus 12, so minus lambda, and then 132, well, 102 minus 132 is minus 30, isn't it? Okay, and so I've got PAX, characteristic polynomial of A, is lambda squared minus lambda minus 30. Can I find the eigenvalues here quickly? Yeah, I think so. Right, so to find the eigenvalues, I just need to solve this guy, right? Set that equal to 0 to find the real roots, right? And so I've got lambda squared minus lambda minus 30 equals 0. Now it turns out, because this is a quadratic equation, you could use the quadratic formula if you like, but it turns out this one factors down nicely. If you have x minus 6 and x plus 5, you get what you need here. So lambda minus 6 times lambda plus 5 equals 0. And so lambda 1 is 6. Lambda 2 is taking off this other one, negative 5. So I can find the eigenvalues really quickly here. And that's end to end, right? So we started with just the matrix A, identified the characteristic polynomial, solved, found the real roots of the characteristic polynomial, and those are the eigenvalues. Right, so as I said, finding eigenvalues using the characteristic polynomial can be challenging, to say the least, especially when A is a larger matrix, like 4 by 4. Even a 3 by 3 can be tricky, right? It just kind of depends on what gets spit out. Right, so yeah, so a lot of if you're, taking a course or something frequently in linear algebra, you'll be allowed to use like more advanced computational aids, and so you'll want to probably use a calculator to identify the roots of these things and even to calculate the determinants. So, okay, perfect. And so that kind of gets us what we need on eigenvalues and eigenvectors for now. So we know what an eigenvalue is. We know how to find an eigenvalue. Once we have an eigenvalue, we know how to find the corresponding eigenvectors. Right, and so remember, the goal of this section of this lecture was to use the knowledge of eigenvalues and vectors to identify corresponding diagonal matrices. And so that's what we want to switch to next. But I think I'm going to go ahead and break this video up into 2 sections just because it'll be a little bit longer otherwise. So I'm going to go ahead and publish a part 2 for the diagonalization topic. Okay, so we'll see you all in a moment.